So today we are now 2 weeks, T-minus 2 weeks until the end of class. We have 6 classes remaining. As you guys know also, you should have seen information about the final exam. Final exam dates and times are now posted. We'll have information about the final proceeding as we know more points. Again, room has been booked, time has been booked. Please make sure you mark it on your calendars. Watch the Canvas page, as we'll have information about the final coming up, including when we're going to have sample exams and other material like that posted to help out leading up to that part. One other quick announcement too. Today we're going to go through chiral properties, work through things of applying things like RNS and comparison of molecules. We've decided the concept, or this topic, Fisher projections, this is one more projection for chiral molecules. It's similar to what we did with Newman projections. It's a visualization standard that can be used specifically in biochemistry. We'll present that material, not here in class. It's going to be a webcam or webcast for that point up for this Friday. That'll allow us a bit more time to work specifically on substitution reactions. This is SN1, SN2. That'll take us into the final part of this course. So, where we left off last time, we've been diving into this topic of isomers. Isomers are different molecules. They have different IUPAC names. And we have these different categories, right? Constitutional isomers, that's the big overall heading. That means that they're very, very, very different. Only molecular formula is the same. Next level down, we have stereoisomers. Stereoisomers, same molecule, very similar arrangement, but the geometry around what we call a stereocenter is different. This is really, really specific because now we're talking about is basically the molecule is really similar, except there is some part of it that we would physically have to break bonds in order to reconfigure it to make some other molecule. Stereoisomers are really close, but still they are different molecules. Not like conformers. Conformers are the same molecule that by rotating single bonds, we can make them look identical to each other. If we had two molecules and we're comparing them, we have these different categories. So over the course of this week, we're going to work through each of these parameters and comparison of two molecules. And remember, the thing about looking at two different molecules, you're talking about familiar relationship, a relationship between two compounds. Some of what we're talking about today, especially this concept of chirality, these are properties of a single molecule. So I'll try to make a discrimination of when we talk about definitions, some of these new names talk about the properties of a molecule. It is chiral. What we're talking about separately, these ideas of stereoisomerism, that's a comparison between two molecules. Like saying your brother or your sister, that's a relationship between two things. And I'll try to identify those as we go through. So one of the hardest parts about talking about this is we have these brand new words, and we're trying to really clarify where these relationships come in. So asymmetric centers, remember, what was special about an asymmetric center? We talked generally about stereocenters. What was special about an asymmetric center?
4 different levels of priority.
4 different levels of priority, more deep than that. Something else, yeah?
Swapping any of the groups would yield a different molecule?
That's a general property of just a stereoisomer, right? If we swap any two groups at some carbon that produces a stereoisomer, we can say that carbon is a stereocenter. For example, I have this carbon, a methyl, a hydrogen, other carbon, let's put a methyl and a fluorine. From this, I can call this carbon and this carbon are both stereocenters. The reason why, if I were to take either of these bonds and change them, I would create hydrogen methyl, where I don't touch the other two, let's say. These two, relative to each other, are stereoisomers. By changing 2 bonds at that carbon, it means that that carbon would be referred to as a stereocenter, broad scope. That applies to any stereocenter. So this is our EZ, right? Asymmetric centers were special for another reason. So 4 different priorities. Yeah, what else? 4 different priorities, but it is on what kind of carbon? What's the hybridization?
sp3.
sp3. The key with an asymmetric stereocenter is it must be on a tetrahedral carbon, right? So these are both stereocenters. But it is not an asymmetric stereocenter. This alkene here is not an asymmetric stereocenter because it's an sp2 center. An asymmetric stereocenter would be something like methyl, ethyl, to the back, hydrogen. Oh, I'm drawing that terribly. To the back, hydrogen, and then over here, let's put chlorine. Methyl, ethyl, chlorine, hydrogen, these have 4 different priorities. It is on an sp3 center. Yes, this carbon, this new one we just generated, it would be called also, that is a stereocenter. Changing any 2 groups at that center would produce a new stereoisomer, but this gets a special name. This is not just a stereocenter, this is an asymmetric stereocenter because it is at this sp3 center. We identify these because having asymmetric stereocenters is necessary to give this emergent property we're talking about, chirality. To be chiral means it has a very defined 3-dimensional shape, and chiral molecules are special because they interact differently with other chiral molecules. Being chiral means it has defined 3-dimensional shape, and more importantly, it has this property relationship where it has a mirror image that is not itself. Your 2 hands, left and right hands, are chiral objects. Your left hand and your right hand are mirror images of each other, but what we say is they are non-superimposable mirror images. In other words, if I try to line up my palms with each other, by doing that, well, my pinky and my index fingers are in the wrong place. My thumbs are in the wrong place. I can't simply rotate my hands to make them perfectly match each other. However, they are mirror images of each other. That is a property of the 3-dimensional relationship and the symmetry that happens in these types of objects. Chiral objects are defined as this point. So chirality is this part. It comes from a Greek word. It means having this property where this molecule, is not superimposable on its mirror image. So this is special because having this property, this emergent property, every molecule that's in this chiral class that can be called chiral will interact specially with other chiral molecules. The demonstration we did last time, the handshake. I have a chiral molecule in my right hand. It will recognize or fit, lock and key, with other right hands. A left-handed molecule will have a very different interaction. So, chiral objects are these things with 3-dimensional symmetry where their mirror images are new themselves. They're mirror image relationships, but they are not superimposable. We cannot simply take your right hand and your left hand and perfectly line up all the pieces. We get 2 out of 3. You know, I can line up either my pinky, my index fingers, my thumbs, those are all good. My palms, though, do not line up. They are actually invert to each other. If I try to line up my palms, now my fingers, my thumbs are in the wrong place. Where this fits, in terms of molecules, is like what we've been talking about our asymmetric stereocenter. Remember, on our typical point here, we say that if this is my lowest priority group, we would cite down this one. Quick question. If I said this was highest, number 2, number 3, I'm holding number 4, what is this stereocenter? RS. If this is 1, 2, 3, this is a R. And then same point, if green is 1, red is 2, blue is 3, this guy is, they are the opposite geometries. Now notice, these 2 guys, if I line them up side to side like this, there's a mirror plane right down the middle. They are mirror images to each other. Also, if I line them up this way, I can say, all right, I'm going to try and line up my red, black, and green. But if I do that, I'm going to have 2 guys out. Blue does not match. The little guy here does not match. They're opposite. I can invert them. If I were to break these 2 bonds and switch their position, I can invert the 2 from each other. But these guys are chiral. Why? At this asymmetry, having this 3-dimensional property, it is not superimposable on its mirror image. One molecule, though, we say a molecule is chiral. Chirality is the property of a single molecule. It is chiral because it has a mirror image that it cannot superimpose on, your left and right hands. Your hand is chiral. The reason it's chiral is because of the comparison to another object. Okay? This is where the naming gets into it. We can have other objects which are achiral, lacking this symmetry property. Achiral objects would be like a simple chair. This chair has a mirror image, the mirror image of that chair is the same thing. There's nothing different. I could take this picture and overlap it with my real object, and they would perfectly line up. We would say in a molecule like this, an achiral object is superimposable on its mirror image. Now the emphasis we place in is this property of alignment or mirror image superimposability. That's where the naming comes from. It was noticing that this property existed. But how we identify it really comes down, especially in molecules, it's focused on the asymmetric stereocenter. You could identify things by having a molecule, trying to draw its mirror image, and then asking yourself, can I overlap them or not? That is one way to identify chiral molecules. A much easier, faster way is to focus on a molecule, find asymmetric centers. If a molecule has 0 asymmetric centers, it will never be chiral. If a molecule has asymmetric centers, it has the chance of being chiral. And we'll talk about this. Again, having asymmetric centers is a prerequisite. You must have asymmetric centers if you ever have a chance of being chiral. But there is, just like all good things, if you have an asymmetric center, you're on the road, but you can still screw that up. You could have asymmetric centers and lose the ability to be chiral. We'll show you those too. But most important, no asymmetric centers, no chance. You must have those. So we'll show you with this property of looking at actual molecules. You could do the mirror image point of it. Much faster, though, is inspect the molecule for asymmetric centers. If you can find those, you're on the right track. If it has none, you are achiral. No dice, you're out. That's the easy part. If a molecule has them, it will be chiral, and then we have this clause, unless it has an internal plane of symmetry. We'll talk about that one towards the end, but let's focus on the first. Most important, chirality is a property of an individual molecule. A molecule is chiral. My hand is chiral. So don't get confused of this thing of, oh, my left hand is chiral, my right hand is chiral. It is chiral because of the comparison, but chirality is a property of a molecule, the same way a boiling point is, the same way that a melting point is, the same way that polarity is. It is a polar molecule or a nonpolar molecule. So think about this. We say it is a chiral molecule because of the asymmetric centers. The property into it is what gives rise to this three-dimensional symmetry. So, here's a molecule. Make the call. Chiral or achiral? Why? Blah, blah, blah. Why? Does it have an asymmetric center?
Yes.
Cool. Next thing you haven't seen yet, does it have an internal plane of symmetry?
No.
It doesn't, and again, we'll look at why, but there is one, does everybody agree, one asymmetric center? Most important thing about internal planes of symmetry. Does anybody know what an internal plane of symmetry is?
Yeah.
What does it sound like? Internal plane of symmetry means what?
A plane where things are the same on both sides.
Yeah, you could take the molecule and reflect part of the molecule with another part of the same molecule. In other words, the plane cuts through the molecule itself. The symmetry we're talking here, the mirror plane, would be beside this molecule, not touching any bonds, not touching any parts. That's the mirror we'd be talking about. If a molecule, it has an internal plane of symmetry, most important, if it has an asymmetric center and a plane of symmetry, it must reflect that asymmetric center, meaning every molecule that has this internal plane of symmetry problem, how many asymmetric centers must it have, odd or even? It must always have even. Again, I'll prove it to you towards the end. My point is, if a molecule has an internal plane of symmetry, it will have 2, 4, 6, 8. It must somehow reflect internal these asymmetric centers. A molecule that has 1, 3, 5 will never have an internal plane of symmetry. And you can, again, that will help to sort of to focus on this. This molecule has an internal plane, or has an asymmetric center, therefore it is chiral. That is a property of it. So by identifying that it has an asymmetric center, we can make the conclusion it will be chiral. How we see that is our property. What about this? Chiral or achiral? I want more confidence. This is why? Oh, well, yeah, like if you look at it, no asymmetric centers, right? We got a bunch of things we could choose. Nitrogen, not an asymmetric center. Hey, we got a carbon here. Is that an asymmetric center? Why not?
The 3 hydrogens.
Same priority on the hydrogens, right? Well, this carbon looks pretty good, but it is what hybridization? So it's flat. This molecule is achiral. There are no asymmetric centers in it. It is a flat molecule. There's nothing going on here. So absolutely, this is not a chiral molecule. What about this guy? Chiral? Achiral. Do you have asymmetric centers? Yeah? How many do you have? So let's start here. Remember, when you're evaluating them, we want to really, what we're saying is, does it have asymmetric centers? Can you give it an R or S notation? Starting on this center here, the one that on red, or sorry, green, we have oxygen, go into the back, hydrogen, and 2 carbons. Who's number 1? Who's number 4? You should be able to pick that one off right away. We got, yeah, oxygen's 1, hydrogen's 4. So we've got a tie between 2 and 3. Right now, we've got over here a carbon, here a carbon. Guy on the right, what is attaching to this carbon here? We have 3 things attaching going forward. We have carbon, hydrogen, and hydrogen. What about the other side? Over here we've got carbon, hydrogen, hydrogen. We are still tied. Move out. We go 1 more carbon down. So now I'm evaluating this one versus this one. This center here is a carbon. This center is a carbon. Still tied. Contents. The guy over here has a carbon, carbon, hydrogen. There are 2 carbons attaching and a hydrogen. Moving out. Over on the left, we've got carbon, hydrogen, hydrogen. This guy wins, which means the whole arm wins. This is number 2. This is number 3. RS. 1. Hydrogen is already to the back. 1, 2, 3. If you put your hand on number 1 and turn to number 2, it's like making a right-handed turn. This is an R center up top here. So we at least have 1 asymmetric center. Let's do the other one. Down here, we have, to the back, hydrogen and a bunch of carbons. So we got number 4. We have the lowest priority group, right? We got 3 carbons attaching to it though, right? Everywhere we go, we have carbon, carbon, and as we did, we've already done this content up here. All carbons. Okay, contents. Over here, we have hydrogen, hydrogen, hydrogen. Up here, we've already done it. Carbon with carbon, carbon, hydrogen, hydrogen. Over here, carbon, hydrogen, hydrogen. Can we define anything? Is anybody winning or losing at this point? Well, we've got number 4. Yeah, we got number 3 now, right? CCH, CCH are tied, but C3 hydrogens, this one here is going to be number 3. We're still tied. Let's move on. So now we've been comparing this guy versus this guy. Let's move out 1 more. At this center, what do we got? A carbon. Down here, a carbon. We've already done this one. It is carbon, hydrogen, hydrogen. Up top, it is what? What are the 3 things attaching to this center now? We have oxygen and carbon and hydrogen. Who wins? Top or bottom? So, number 1, number 3, number 2. If you put your hand on number 1, lowest priority is already away from you. Put your hand on number 1, right or left turn to go to number 2. So this is a S center. Do we have more than 1 asymmetric carbon? Yes. Is there an internal plane of symmetry? If you looked at this molecule, is there anywhere I could drop a mirror on this molecule to reflect the top half to make it look like the bottom, or left half with right? Is there anything that gets close? Well, look, you look at the OH and the methyl, they're both up, but oxygen and methyl are different. In other words, if I put a mirror right through the middle of this, sort of across this part of the plane here, and I would try to reflect one versus the other, oxygen, methyl, do not blink, there is no internal plane of symmetry. This molecule has two asymmetric centers, one is an R, one is an S, and it has no internal plane of symmetry. It is chiral, absolutely. How would you name this? So yeah, let's start at the root. Biggest carbon chain, this is how many in the longest carbon chain in this molecule? 6. So it is a hexane, but it's not just hexane, it is a cyclohexane. Okay, but it's not just a cyclohexane. What's the functional group as part of this? This is a alcohol, so it's not a cyclohexane, it's a cyclohexanol. Good. And if we're calling it, if this is now a cyclohexanol, we've decided that is the property, the spirit, the identity of this molecule is cyclohexanol. Where does the numbering have to start? We change the end of this. So what is number 1? Yeah, right there, where the alcohol is. So this is a cyclohexanol, which means carbon number, what? 3 or 5? How would we number this?
3.
Yeah, this is better, 2, 3. Carbon 3 has a what attaching to it? Right, so this is a 3-methyl cyclohexanol, or cyclohexan-1-ol, or whatever, right? Like you could add the 1 into there if you want to be specific. Probably don't need it based on how you've named it. Cyclohexanol means carbon 1 is going to have that alcohol, right? Okay, it is a 3-1 sort of system. What did we say the chirality? Chirality, RS notation at the top here. This was R, down here was. So at carbon number what is R? Carbon number what is S? Yeah, 1 is R, 3 is S. So it is a 1R, 3S, 3-methylcyclohexane, 1-ol.
Sorry.
I don't know why Siri loves doing this. Does that make sense? Individually build up different pieces. Sequentially build up your naming. Do your RNS and then through here. The property of chiral or not can be helped by this, mainly because you're looking for these RNS notations. If a center can be given an RS notation, it is an asymmetric center. Okay. That's how we deal with identifying chiral molecules. Find those asymmetric centers. Here's the caveat. So this is where you look through a molecule. If a molecule has no asymmetric centers, it's not chiral. Never was, never will be. If a molecule has asymmetric centers, hold your horses. It's on the right track, but we have to look for this. There's a possibility that if a molecule has a plane of symmetry through it, in other words, if we put a mirror on the molecule that actually cuts the molecule itself, reflects left half and right half, this is what we mean by an internal plane of symmetry. And if you notice, what's happening here is that an asymmetric center? Does it have 4 different priority groups? Yes. Yeah, fluorine, ethyl, some big long chain, hydrogen. That's an asymmetric center. What about the other side? Is this an asymmetric center? Could I give it an RS notation? Yeah. What happens? The thing I want you to pay attention to. The molecule has asymmetric centers, but it has a plane of symmetry that is reflecting that asymmetric center. The 2 different asymmetric centers are bisected by this plane of symmetry. As a result, molecule has two asymmetric centers, but the geometry of those asymmetric centers as it moves through the mirror plane, what happens to it? If it was R over here and you have a mirror, what must this one be here? Yeah, if you move through the mirror plane, an R will reflect as an S. Yes?
So when you're counting the priority groups, do you count the, do you use the mirror plane and make them 2 separate molecules, or do you just include other branch with the F3 molecule?
When you're counting if what their priority is, You simply move out carbon by carbon. You don't even need to look if the mirror plane is there. What we're saying is, if I were to rank this carbon versus this carbon, there may be no difference. They're both CHH, right? But going out one more, comparing these two, methyl will lose to this one, right? So we just keep moving down the lane. Our assignment of R and S in terms of the priority does not even pay attention if the mirror plane is there. We continue along like we've normally been doing. What I'm trying to draw your attention to, these mirror planes are easily identified because molecules that have asymmetric centers and mirror planes must have even numbers of these asymmetric centers, because the mirror plane must reflect that one somewhere else. More importantly, if one is R, the other one must be S. If you notice that, two centers, same stuff attaching, one R, one S, pay attention. That is the hallmark of you are probably dealing with a meso compound. Yeah, sorry, question here. Yeah, that's a really good point. If this was a wedge, like if I drew this, same molecule, one is a dash, one was a wedge, does this have a plane of symmetry anymore? If the fluorine was down, but I now put this fluorine here up, do the left and right hands, are they perfect mirror images of each other? No. If I do this, what I'm saying is the left and right hand pieces have to be, so me, right? If you bisect yourself down here, this half and this half are exactly mirror images of each other, which means I have a plane of symmetry down the middle. I'm a meso compound. If I do this, this half and this half are no longer mirror images to each other. The geometries are different. This one reflecting is nothing up here. This one reflecting nothing down there. This is a chiral molecule now. So if the geometries are such that if this was one was down, one was up, we've broken that mirror plane. It is not a perfect mirror image left and right anymore. So what about this? Is this chiral? Now again, start through your ranking. Does it have asymmetric centers? Yes. I can give an R and S notation to 2. How many asymmetric centers? 2, right? So this is where, if you see this, I have 2 asymmetric centers, your radar goes up. I have an even number of asymmetric centers. Look at them. This one has chlorine, chlorine. Wow, this is starting to look really similar. More importantly, this one is up, as is this one. If I put a mirror plane down the middle here, one half the molecule, the other half the molecule are the same. They're a reflection of each other. So is this molecule chiral? No, this molecule is meso. So if you're trying to redo the ranking, step 1, does it have asymmetric centers? Good, you're on the right path. Number 2, is there a plane of symmetry? How you check it? How many do you have? Are they even? 2, are both asymmetric centers same stuff? If one's a methyl, one's an ethyl, you're good to go. If one's a fluorine, one's an oxygen, no problem. If they're both chlorines and they both have this repeating geometry, if you go through this, one of these is going to be R and one is going to be S. That is the hallmark of a meso compound. This guy's meso, it is a chiral. Now why does that happen? Remember, to be chiral, it cannot be superimposable on its mirror image. Draw this guy's mirror image for just a second. So if I put a mirror here, I'm going to reflect this. So I'm going to draw, this is up, chlorine, and then up here, up, chlorine. That's the 2 molecules. The molecule we had, the mirror image we created, are these the same thing? Can I rotate this molecule in such a way to overlap all of the molecules? All the different parts of it? If I were to take this chlorine here and line it up there, this chlorine here, line it up there, that's possible by just rotating this down, rotate this up. If I physically took the cyclohexane and just spun it, I would get that's blue, that's orange. Remember, they're both chlorines. I've tried to locate them. Oh, sorry, I messed up my colors. Boop. Doop. My point is, they're just chlorines. There's nothing that makes one chlorine different than the other. So geographically, how we set it up originally, if I move this one up, there's my blue, there's my orange. They perfectly line up with how we started off here. As we move through the mirror plane, the designation of these centers, a chlorine is just a chlorine, carbon is just a carbon. By rotating the two, we can line them up perfectly. It is superimposable on its mirror image. That's a property. It happens because of this internal plane of symmetry. Its mirror image is just the same molecule back again. So it's like looking at the chair. The mirror image of the chair is just the chair. How does that feel? Again, naming. A molecule is meso. This is meaning to say it has asymmetric centers, but it is achiral because of some internal property. Where you can sort of watch this out, though, is IUPAC naming can help you. If a molecule has these two, if I were to draw its mirror image and I were to name it by IUPAC naming, what you'll notice is they have exactly the same IUPAC name. The numbering would be the same. The RS notation would be the same. Yes?
Wouldn't the RS notation change because the counting would change?
Your counting would change, but again, how would you decide to count this?
Yeah.
This is number 1, this is number 3, right?
Yeah.
Down here, 1 and 3. You would choose the counting that gives you the lowest priority, so it's still going to be 1 is 1, 3 is 3, R and S is R and S, right? It all lines up. So again, a molecule is the same molecule if the IUPAC name does not change. And this is why relying on IUPAC and RS can really help you, because it does not matter how you draw it. When a molecule is lined up like this, it can't rotate. There's no other conformers that are possible. It becomes a little easy to see, oh, there's a line that draws through here, top and bottom half reflect. This is a meso compound. What about this guy? Chiral, achiral, meso. Does it have asymmetric centers? Yes. Okay, how many does it have? 2. Does it have an internal plane of symmetry? Can I draw a line that makes one half look like the other half? Right through there. If I were to put a mirror right through there. Now the important thing about this plane of symmetry, the plane of symmetry can draw through atoms in a molecule or through bonds in a molecule. The point of the internal plane of symmetry is you're drawing a line that cuts the molecule somehow. So top half and bottom half of the molecule are the same. They do have asymmetric centers, but because of the plane of symmetry, it is meso. Yes?
It's in that it's achiral and
It is achiral, yes, but it is achiral because it is a meso compound. What we mean by meso is really saying you did a good job. You've got asymmetric centers. But I'm sorry, you don't get to play with the chiral guys. You are not chiral. You don't act like a chiral molecule. You don't interact with chiral molecules the same way. This is Rudolph. Okay? No reindeer games. What about this guy? Chiral or achiral? Does it have asymmetric centers? Okay, so it's not just achiral. If it's achiral, it's something to do with meso, so we've eliminated that one. Yeah, it's got asymmetric centers. How many? Yeah, both of those methyls, those matter. They have different priorities if you go around them. If you extend out long enough, you will get R and S notation. But if I had to try and form a mirror plane down here, that would be my plane, left and right half. This methyl up does not correspond to that methyl down. It's not a mirror. It's a rotational option, right? So, chiral or meso?
Chiral.
Chiral, absolutely. This is a chiral molecule. This guy's chiral because it has asymmetric centers, no internal plane of symmetry, chiral. Again, these are small geometric differences, and we focused right now on cases where those centers cannot change. We're talking about decorating a cyclohexane ring, which is rigid, right? The thing I want you guys to practice in the problem set we created for this, we gave you many other options where if I were to cut this ring right here, they are no longer attached. This can get much harder because now conformers can rotate such that this molecule may not look as easily laid out like this. Molecule is meso if in any conformer this symmetry property exists, not just because of how I decided to draw it. What I mean by that, let's go back to our first example. This guy. So as we've discussed, we have asymmetric centers. We have a plane of symmetry. But the visual test for plane of symmetry we did by saying the molecule as lined out with the carbon chain side to side, the two fluorines presented nicely. We've arranged the molecule in such a way that we're presenting that plane of symmetry. If I were to simply rotate this bond, if I were to rotate this bond, let me try to draw that. What I mean is, here, fluorine, and we're going to rotate this so this is up, which means it's going to look like this now. Whoops. Yeah, good enough. All I've done is rotate this single bond, right? It's a different conformer. Did I change the RS notation at that center just by rotating this bond? Is it still R or still S? By rotating a bond, you do not change priorities. You do not change anything else. It's like saying, here's my right hand, still my right hand, still my right hand. I'm just moving it in space. Even if it's drawn like this, where the plane of symmetry is not immediately obvious, this is still a meso compound. It is still a chiral. Because, just because it's laid out like this doesn't mean the molecule in some conformation has this mirror plane. This is what makes this tricky from a visual perspective. That's why I emphasize, look through your molecule. If you find asymmetric centers, you're looking for 2, 4, 6. When you find your asymmetric centers, you're looking for common groups, fluorine on one side, fluorine on the other, ethyl on one, ethyl on the other. And third, you're looking for an inversion. If one asymmetric center is R, the other asymmetric center is S, that is starting to qualify. You may have a mirror plane. If one is S and the other is S, you're good. There is no way that can be a mirror plane because both asymmetric centers have the same geometry. S and S through a mirror plane, one has to be S, one has to be R. So this is where relying on finding them, doing the assignment will help you so much more than just visually looking at it and going, oh yeah, that's not meso because there's a methyl one way. Don't get caught. Yes?
For the fluorine on the right, that's rotated, is there a wedge?
Excuse me?
Like, because it's rotated, so that it's a wedge for fluorine?
Yes, this is a wedge now. If I were to take that center here, and mentally what I'm doing is I'm saying I take this one. If the fluorine was back, and I were to flip it, fluorine that was, to you guys, fluorine was back, gets rotated, woo! It's out towards you now. This is where your model kits are your absolute savior also. Yes?
Where's the mirror plane?
In this geometry,
Yeah.
you cannot see it. That's what I'm saying. In a conformation, a mirror plane may not be obvious. It's still there because if I were to take the molecule drawn like this, rotate it, I can now make the mirror plane show or appear. If a mirror plane exists in any one conformation, the whole molecule lost its chirality. That's why. Okay? Yes?
So when looking for chirality, it'd be good to set up a molecule and then just rotate it so you can see a mirror.
That will really help. Physically playing with the physical molecule can help you a lot with this point. If your left and right half look identical, it jumps out at you much quicker too. Okay? Okay. Yes?
Do the conformers exist as separate structures like found organically?
Say that one more time.
Do the conformers exist as separate structures like they're found in like identifiably separate as opposed to like resonance structures where it's like one to one?
Really good question. Do the conformers exist as separate structures? The answer is yes. In other words, if I had some magic way of separation, I might be able to physically separate or hold on to one conformer, not another. Because remember, there's a barrier of rotation, an equilibrium. This is like when we talked about cyclohexanes, we have the axial equatorial presentation. Those are physically distinct objects, not like resonance structures. But the property of chirality is an average over all. One conformer might miss this plane of symmetry, but on average, it will still sample ones that have no symmetry. Yes?
So like if you have a sample of a substance, at any given time, there can be any number of monomers existing simultaneously.
Exactly. If you had a sample of the substance, you've got an energetic distribution based on Boltzmann that says whatever the lowest energy was probably your major. If you were just throwing darts at it, the lowest energy would be your maximum probability, but all of them are possible. Remember, when we talked about cyclobutane, the rotations, that's only 4 or 5 kilocalories. The energy we deal with at room temperature, RT, is hundreds of kilocalories. Plenty of energy to allow them to rotate. So they are all being sampled rapidly. Any other questions on this? This is by far the biggest mental gymnastic thing that you guys have to go through. Practicing it requires both the drawing aspect, nailing to this thing, relying on your RS notation, your IUPAC naming, and your model kits. But it comes with time. I definitely stick with it. So recap. All of isomers. We determined that all isomers, we have stereocenters. Stereocenters are talking about carbons that give rise to isomers, stereoisomers. And we have two really big kinds of stereocenters, EZ, RS. RS stereocenters are our special kind in them here. These are asymmetric stereocenters. Asymmetric stereocenters are the ones we're watching when we talk about chirality. If a molecule has an asymmetric center, it's either chiral or meso. It's one of those two. No asymmetric centers, you're already achiral. So process of elimination breaks it down from 3 to 2. If the molecule has asymmetric centers and has 1, 3, 5 asymmetric centers, could it ever be meso?
No.
No. So this is why correct identification of your asymmetric centers is so popular, because it can really, really quickly say, if you have odd numbers of asymmetric centers, you're already on the path of being chiral, not meso. If you have 2, 4, 6, pay attention. You may have a meso compound. You have to look deeper. So what this now means, if you look at any two molecules, now that we've got these classifications, molecules are chiral, achiral, or meso, we can look at them and say all molecules can be classed at these kind of different designations. There is no relation. They're just molecules. They're stereoisomers. Under stereoisomers, we have these other two that we're going to discuss. Special names, enantiomers and diastereomers. Constitutional isomers, these are same formula, different arrangements. And then we have identical. Identical means conformers. Same molecule that can rotate into each other. So the two big names that are new here are these classifications, what we call enantiomers and diastereomers. These are how we designate the relationship between stereoisomers. So if you looked at these guys, first of all, from the hip, compound 1, compound 2, is there anything that relates to those guys? Stereoisomers, enantiomers, well, stereoisomers, conformers. Is there anything that makes these two guys similar? Are they even isomers? Why not?
One has a double bond.
Okay, what does that mean?
It means it's got one less hydrogen.
One less? You just failed. What's the formula difference between middle and end? How many hydrogens different? 2 hydrogens. They don't even have the same formula. These are not related. These are two awesome molecules passing the night. They have nothing to do with each other. What about the next two? Middle and side, isomers, conformers. Is there anything that relates to them? Same problem, right? They're different molecular formulas. If you have different formulas, you are done. So you start up at the top. If you have different formulas, we're not even talking about isomers. What about these two? The outside two. They're constitutional isomers. Why, though? Does that make sense? Yeah. Yeah, same hydrogens, same chlorines, same carbons. The difference, though, is one is a, what would you call this? The 2-chlorine? This is a bleu dichloro. This is a 1,3-dichloro. This is a 1,2. They are on totally different carbons. This is 1,3. This is 1,2. They are constitutional isomers. So we move towards levels of more similarity. These are the farthest ones. What about these? All three of these molecules are what? They're identical. They're the same molecule in different conformations, perspectives, or orientations. The IUPAC name for each of these would be identical. Does it have an RS center? Does one molecule have an RS center? Yeah. Do they all have the same RS geometry? Yeah, maybe. Left and right. The left and middle. Same? Did I change RNS just by flipping that center of the methyl? No. When I go to the guy in the end, how did I go from left to the guy on the right? What do I have to do? Yeah, pancake flip, right? If I take the molecule, oxygen is out towards you, and I flip it over, oxygen's in there, the whole molecule's end over end. You've converted it this way to get to that structure. These are identical molecules in either different orientations, perspectives, or conformations. No change. And again, you can tell that by their IUPAC names. They will be common. What about these? Same molecule, constitutional isomers, totally unrelated. What do you got? Okay, so let's start at the top. Same formula?
Yeah.
Okay, so they're isomers, right? Do they have chlorines, hydrogens in the same relative places? It's a 1 what dichloro? They are both 1, they're both 1,3 dichloro. Cool. How do I go from the guy on the left to the guy on the right? What might I do? This. What is that called? Chair flip. This is what? When you move cyclohexane from a diaxial to a di-equatorial, do they have different IUPAC names? No, they are just conformers of each other. They have the same, they're both 1,3 dichloro. If we were to go and name them, we would have similar names on both cases. But all we have to do to interconvert these two is a chair flip, single bond rotations, identical, same conformation. It's when we get here to stereoisomers. If we've eliminated that process, they have the same formula, they have the same connectivity. They actually have to, there's not just a simple rotation that I can do. This is where we're in that category of stereoisomers. When we're in stereoisomers, there are two names that you have to identify. Once you're down at stereoisomers, they are either, and it's not disastereomers, it's diastereomers and enantiomers. So this is what we're going to kick off next time. Now first off, does anybody know, has heard of thalidomide? One. So this is your terrible story for the end of the day. There's a drug that was administered as a painkiller many years ago by the Germans. Has anybody heard of thalidomide? Yes? Thalidomide was this amazing wonder drug that really helped with pain. It helped with upset stomachs, with morning sickness. The problem with it is one enantiomer, one geometry looks like your right hand, does a wonderful thing. It helps you. The exact mirror image molecule prevents the growth of limbs in babies. This was the worst way to figure out how chiral molecules work with people. We're going to kick off this last time.